Ngalakin Khadijan Nyunga Boja.
Video 12, Relational Algebra. So, relational algebra is a very traditional component of courses on relational databases. So, relational algebra is basically the mathematical theory on which the practice of relational databases is built. It is, in its full form, it's quite technical and detailed and quite difficult. It's useful for theoretical discussion about relational databases, but it's not really important for practical use of relational databases. So this unit is more concerned with practical use, and so I'm not going to go into relational algebra in great depth, but I'm just going to give a brief overview of it. The idea is that you just get some idea of why relational databases are the way they are. Okay, so let's just think about what algebra is. So algebra, an expression in normal algebra, is something like this, where x and y are variables that are presumed to stand for numbers, and they're combined by operators like plus and minus and times. We all know that if we choose a specific number for x and y, x equals 2 and y equals 3, then you can evaluate that expression and the value itself will be a number. Now, the main benefit of algebra is that there are various rules which show you how you can manipulate algebraic expressions. Here's a very, very simple example. X squared minus y squared is equal to x minus y times x plus y. Now that means that in any calculation or computation, you can always replace x squared minus y squared with x minus y times x plus y. Okay, you'll always get the same value by doing that, but in certain circumstances, one of those two things might be easier to compute than the other. Like you may already have computed the values of x squared and y squared, in which case you can very quickly calculate x squared minus y squared. So the computer then has the freedom to choose whether it wants to evaluate x squared minus y squared or x minus y times x plus y. So in general, we have no idea which of those two might be easier to compute, but the point is that the algebraic rule shows us that it doesn't matter which one of those we do calculate. The whole point of relational algebra is that the same things apply when x and y are not variables that refer to numbers, but we have variables that refer to relations or tables. Okay, so mathematically then, a relation is just a set of tuples. So remember that a tuple is a thing a bit like a vector that has a value in each of several different coordinate positions. So here's a table called R. Now it's got 3 columns and they're called A, B, C. So sometimes we'll write this relation R, A, B, C. That just shows the name of the relation and the name of the columns. Here are the tuples in this relation. The first row has 1 for A, 0 for B, 1 for C. So as a tuple, that's 1, 0, 1. And then the second one is 2, 1, 1. And the third one is 1, 3, 0. Okay, so mathematically then, a table is nothing more than a set containing the rows of the table. Okay, so now let's think about what a legal expression in relational algebra is built from. Well, you have variables that represent relations. So like the R that we saw from the previous slide. You have various set theory operators, which are just like the operators in set theory that we did at high school. Things like R union S or R intersection S, I'll explain a bit more about what these are in the next slide. And then we have some relational operators, which are new operators that do things that are sort of related to relations rather than just sets in general. So every legal expression in relational algebra, you can evaluate it by putting an actual table in for R, an actual table in for S, and the output will be another table or another relation. I'm only going to do really, really simple examples. Okay, here's a simple relational algebra expression that just uses union. So what does R union S mean? Well, it means the rows that are in R or that are in S. I'm going to show you a particular S shortly as an example. Okay, so that's an expression and we know its value and it is R union S. Now here's an obvious identity. R union S equals S union R. If we're going to put together all the rows of R and S, then it doesn't matter whether we do the R's first and then the ones in S or vice versa. Okay, why might this identity be useful? Well, it just means that the query optimizer can choose whether to do R union S or S union R, and it's guaranteed to get the same answer. Okay, now that's sort of a trivial example, but the point of it is that when you issue a query to SQL, the system examines it and sees whether it can rewrite it into an equivalent legal expression that's better to calculate. So it uses in the background these rules of relational algebra to redo your query, to turn it into something that might be inefficient into something that might be more efficient. Okay, let's just illustrate this actually in SQLite. Well, this is SQLite Studio. So the first two lines, I've created two tables. One's called R and one's called S, and they've both got 3 int values. So R has got values columns A, B, and C. S has also got columns A, B, and C. Whoops, I don't think I wanted that. Well, A, B, and C. What are the values in R? 1, 0, 1, 2, 1, 1, 1, 3, 0. So I've actually just filled it up with some sort of sample data, just for illustrative purposes. Okay, what is the union of these two sets? So we're going to take any tuple that is in either R or in S. So R union S is, well, it contains 1, 0, 1. It contains 2, 1, 1, because that's the second row of R. It contains 1, 3, 0, because that's the third row of R. Now we start putting the things in S in. Well, 2, 1, 1 is already in our relation R union S. So because these are just sets of tuples, then we only can include it once. So 2, 2, 2 and 3, 0, 0. Okay, you can actually do that in SQL, just that exact relational operation in SQL. Select everything from R, union everything from S. And what we get is indeed exactly the 5 rows that we expected to get. Okay, so the union operator of SQLite is just the union operator from relational algebra. Intersection. Here's another expression in relational algebra using the operator intersect. And so R intersect S is the table formed by any rows, any tuples that are in both R and S. And of course, we have this identity that the intersection of R and S is the same as the intersection of S and R. Now, this is a bit more useful because when it's computing R intersection S, the computer knows that it can either look at every value of R and check that it's in S or not, Or it can do it the other way around. Look at every value of S and check whether it's in R or not. So here, there may be some actual benefit in replacing R intersection S with S intersection R. The relational algebra tells the computer, tells the implementation, this is a safe thing to do. This is a mathematically correct thing to do. You will not accidentally make the answer wrong by making this alteration. Of course, we can do this in SQL as well. If I do select star from R, and then I intersect it with select star from S, I get the rows that are in both R and S, and the only row that was in both R and S, the only tuple that was in both R and S was 211, and there it is as the sole row of the output. Okay, who needs to know relational algebra? Most database users can get by without it. Database developers, like people who are developing complicated queries for other people to use, may find it useful to think in a sort of relational algebra way. People who actually write the databases and write the query optimizers, well, they really need to use it in order to do this query optimization. Now, at this level, we don't know whether you're going to end up being a database user, developer, or implementer, but probably, most likely, you'll be a database user. And so really, you don't need to know the details, except that you should know that it exists, and you should be able to recognize it when if people talk about relational algebra. Okay. Now let's look at some of the operators. For normal algebra, we have the operators, the arithmetic operators, plus, minus, times, and all that. Then we got the set theoretic operators, which are union, intersection. And now we have two special relational operators. So there are two important ones. One is the projection operator, pi, and that's the Greek letter pi. If you have to write something in a test or exam that uses pi, just type in pi. Then there's the selection operator sigma, that's the Greek letter sigma. And then again, you just type in sigma if you need to type something in a test. Okay, how do these two things work? Well, pi stands for projection, and that means that a relation is projected onto a subset of its columns. That means you just choose some of the columns, delete everything else. Sigma deletes some rows, or rather, it keeps some rows. So you choose some rows based on a condition, and those are the rows that survive, that form the output of the selection operator. Okay, how does projection work? So suppose that R is a relation and C is a list of column names. Then this is how you refer to it. Pi sub C is apply the operator pi with the list of variables C to the relation R. So the R is the input, the pi sub C is the operation, and what's left is the relations, and this should say rows. Example, suppose that R is the following relation. So it's got 4 columns. They're called customer id, name, address, and account manager. Then the customer ids are numbers, the names are strings, and so on. So it's just a silly little sort of address table. Okay, what happens if we do pi, and then here is my list of columns? All that happens is we only keep the columns customer id and name. So we keep this portion of the table. That forms the new table. All the rows, only the specified columns. So in this case, we've projected the relation onto the 2 named columns, and we get a relation with fewer columns. May have the same number of rows, or it may have a slightly fewer rows. Let's do another projection. Now we'll just project only onto the name field. Okay, so let's go back to here. So the name field, so that means we will save only this part of the relation. But now this has got some duplicate values in it. Bunnings appears twice, mitre 10 appears twice. And so duplicate rows are removed from a relational algebra expression. And so we end up with this, this relation with one column and just 4 rows. Now, it should be clear to you that there's a direct relationship between pi, the projection operator, and selecting from a table, the select columns from statement. The only difference between the relational algebra expression and the SQL expression, so relational algebra, SQL, is that it won't remove duplicate rows. So trying to ensure that a table never has duplicate rows is an incredibly expensive computational operation. And so almost all implementations of SQL don't remove duplicate rows. They expect the user to manage that possibility. Okay, so projection extracts columns and selection therefore extracts rows. And the selection operator is called sigma. And this is a relational algebra expression involving sigma. Whoops, want my highlighter. So again, this is the input to the expression. Sigma says it's a selection operation. B is a Boolean condition. The way it works is that for each row of R, the Boolean expression is evaluated, and if it's true, then that row is part of the output. So here's a silly example. Here's a Boolean expression. Customer ID is less than 1300. So this is going to select from the table R all of the rows that satisfy the customer ID is less than 1300. These rows all have customer IDs that are less than 1300. The other rows don't, and so those are the only 2 rows the only 4 rows that survive. Now we can build up more complicated expressions by composing operators, by applying pi after applying sigma. So let's see what this expression does. R is our input relation. The first thing is it selects only the rows that relate to Bunnings. So most rows get thrown out. The rows relating to Bunnings are kept. Then the result is projected onto the account manager column. And so what we get is just a list of Bunnings account managers. That's all. Okay. This, if you do it step by step, like I just did, then this is not very difficult. Somehow, though, Greek letters are sort of almost guaranteed to scare students away, and a lot of students sort of throw their hands up and say, I can't possibly understand this. But in fact, it's really is just a case of looking at it step by step and doing it like a computer would do it. Okay, now obviously the Boolean condition in an expression involving sigma is exactly the same as the where statement of SQL. So the terminology is a little bit unfortunate because pi is projection, and what that corresponds to in SQL is the select statement. Sigma is selection, and that corresponds to the where statement. So we've got a bit of an unfortunate terminology clash here because selection in select in SQL is not relational algebra selection. So these two things are not equal. Okay, and then we can build up arbitrarily complex Boolean expressions by adding the normal logical operators and an or, and comparing attributes against constants or attributes against other attributes, and so on. This slide says almost nothing. It's just a fancy way of saying that you can do things like saying, let's say we do selection A less than B of R. So that's going to take the relation R, which had attributes A, B, and C, and we're going to select out only the rows where A is less than B, and that's that sigma. That means it's a row selection operation. Okay, so we will come back and do a little bit more of relational algebra, but for the time being, all that I would hope you'd be able to do is to, if I give you a relation and a desired sort of output, you should be able to construct the relational algebra expression that has that value, and vice versa. If I give you a relational algebra expression and an input relation, then you should be able to evaluate it. Okay? If you really struggle with the Greek letters and sort of the fairly novel way of thinking, then put this on the, put this low on your priority of things to understand. It's not going to be heavily examined. It will be slightly examined, but don't spend too much of your time on it if you can't get it, because most of you will not need to use it on a daily basis.